We begin section 5.4, area and the fundamental theorem of calculus. For the purpose of this section, I won't actually explain what the fundamental theorem of calculus is or how to find area under the curve. Instead, I'm going to link a video by 3 Blue 1 Brown, which does a far better job of explaining the concept than I ever could. I'll just work through examples, assuming you already understand the concept. If you haven't watched that video yet, go watch it first and then come back. Let's begin by calculating the integral from 0 to 3 of 4x dx. We begin by calculating integrals as we always do. We just apply our standard power rule. So we raise the power by 1 and we get x squared, and then we divide through by that new higher exponent. So 4 over 2 x squared, and we evaluate that from 0 to 3. This is how we write evaluated from 0 to 3. We draw a vertical line, the smaller number at the bottom and the bigger number at the top. So the integral from 0 to 3 of 4x dx is 4 over 2 x squared evaluated from 0 to 3. And when we have this evaluated from 0 to 3, that's the same as 2x squared evaluated from 0 to 3, which is 2 times 3 squared minus 2 times 0 squared, which is just 2 times 3 squared, which is 2 times 9, which is 18. Let's look at another example. We want to find the area bounded by the x-axis in the graph of f of x equals x squared minus 1, where x is between 1 and 2. So, like we've already learned, the area under the graph is the integral, which is pretty crazy, but that's just the way it is. So if we want to find the area bounded by the x-axis in the graph of f of x equals x squared minus 1, what we need to do is we need to evaluate the integral of x squared minus 1 between x equals 1 and 2. This is dx because it's with respect to x. And so this is going to end up looking like 1/3 x cubed minus x evaluated from 1 to 2. And so we plug in 2 and plug in 1 and subtract the difference. So this here, this 1/3 x cubed minus x evaluated from 1 to 2 is just 1/3 times 2 cubed minus 2, all in parentheses, minus 1/3 times 1 cubed minus 1, all in parentheses. We're subtracting that entire quantity. So this becomes 8 over 3 minus 2 minus 1/3 minus 1. And so this negative distributes out to everything, and so we get 8/3 minus 2 minus 1/3 plus 1. And so that works out to be 7/3 minus 1, and that works out to be 4/3. And that's your final answer. For this example, we want to evaluate the integral from 0 to 1 of 4t plus 1 squared dt. And for this example, we need to do like we did earlier and multiply by 1 in a clever way. So we can multiply by 1/4, integral of 0 to 1, 4t plus 1 squared times 4 dt. And now taking the integral yields 1/4 times 4t plus 1 quantity cubed over 3, evaluated from 0 to 1. So keep in mind, this is 1/4 times this whole thing evaluated from 0 to 1. So what that's going to end up looking like is 1/4 times 4 times 1 plus 1 cubed over 3 minus 4 times 0 plus 1 cubed over 3. So the evaluation here, the evaluating from 0 to 1, is happening inside that parentheses there. And so this will be 1/4 times 5 cubed over 3 minus 1 over 3, which is 1/4 times 125 over 3 minus 1 over 3, which gets you 124 over 3, which works out to be 31 over 3. All right, let's take a look at another example here. We want to evaluate the integral from 0 to 3 of e to the 2x power dx. As we recall, anytime you have something that's not strictly x in the exponent of an exponential, we need to use u substitution. So here we let u equal 2x, then du equals 2 dx. So then dx equals 1/2 du, and we make that substitution. And we end up with the integral from 0 to 3 of e to the u times 1/2 du, which is 1/2 the integral of 0 to 3 eu du. So we get 1/2 times e to the u, evaluated from 0 to 3. Now, one thing to be careful of here is u is not going from 0 to 3. X is going from 0 to 3. So let's rewrite everything in terms of x before we actually do the solving. We have to do that. And when we do that, we get 1/2 times e to the 2x, evaluated from 0 to 3. And so that will end up being 1/2 times e to the 6th minus e to the 0, which you can plug that into a calculator and you'll get 201.21, or thereabouts. All right, let's take a look at another example. We want to evaluate the integral from 1 to 2 of 1 over x dx. As we recall, the integral of 1 over x is just the natural log of x, so this ends up being the natural log of x evaluated from 1 to 2, which is the natural log of 2 minus the natural log of 1. And if you plug that into a calculator, you get about 0.69. That being said, I'm also totally happy if you leave it in this notation, or if we apply our rules of logs, the natural log of 2 minus the natural log of 1 is just the natural log of 2 divided by 1, which is just the natural log of 2. And if you want to leave it in that notation, I'm totally happy with that as well. All right, let's take a look at one final example. The integral from 1 to 4 of minus 3 times the square root of x dx. Let's go ahead and rewrite this in exponential notation. So that's the integral from 1 to 4 of minus 3 times x to the 1/2 power dx. And we would do what we've always been doing. We add 1 to the exponent, and so we get x to the 3/2 power. And then we divide this coefficient, this -3, by the higher exponent 2/3. So that means we're going to end up multiplying by the reciprocal. So we get 2/3 times -3 times x to the 3/2, all evaluated from 1 to 4. This thing here ends up simplifying down a bit, and we end up with minus 2x to the 3/2 power, evaluated from 1 to 4. Now if you plug in 4 and 1, we get minus 2 times 4 to the 3/2 power, minus -2 times 1 to the 3/2 power, which that simplifies down to be minus 2 times 8, minus -2 times 1. And so we get minus 16 plus 2 equals minus 14.